Welcome back to Fresh Thinking by Snowden-Optiro, the podcast where we unpack the technical realities behind modern mining projects and resource estimation. My name is Senzeni Mandava. I'm joined today by Melanie, Bulley, our senior geologist here in Bristol offices for Snowden-Optiro. Glad you could join us today.
Thank you.
Yeah. So today we're diving into a topic that's become increasingly important as the industry pushes towards reprocessing, ESG outcomes, and critical recovery. That is tailings mineral resource estimates. So now on the surface, a tailings resource estimate might sound straightforward. The ore's already been mined, crushed, and deposited in one place. Surely that makes things easier, but not exactly. Tailing facilities are some of the most technically nuanced and misunderstood ore bodies in the mining industry.
Yes, this is definitely one of those topics where people assume it's simple until they actually work on one.
Yeah, exactly. And I think that's the perfect starting point. Because here, what happens is that most people think that the material is already on the surface, so it's already crushed, it's been processed, so there's no geology anymore. But the reality is that tailings introduced a completely different set of technical problems. So let's start with a big conceptual difference. How should people think about tailings, a tailings facility compared to a conventional in situ deposit?
So the biggest material mental shift is this. A tailings facility is not really controlled by geology anymore. It's controlled by depositional engineering. In a traditional ore body, your continuity comes from lithology, structure, alteration, mineral processes, the natural geological controls. In tailings, those controls are largely destroyed during the mining and processing. Now your continuity is governed by discharge locations, slurry transport, hydraulic segregation, grain size sorting is a really big one, and depositional cycles. And one of the main things is the historical plant operations as well. They can change on a day-to-day basis, depending on who's running the plant. So instead of modelling geology, you're effectively modelling an engineered sedimentary environment.
Absolutely. So, which is a really interesting way to frame it, because you're less of a classical exploration geologist, but more of a hybrid between a sedimentologist, a process engineer, geotechnical engineer, and a historian as well.
Exactly. Some of the most important data sets on a tailings project aren't geological at all. They're old plant records, the deposition schedules, survey plans, the cyclone configurations, so the split between fines and oversize, historical recovery data, and even anecdotal operational knowledge from past site personnel I found really hugely beneficial in the past. That's a huge shift from a conventional MRE workflow.
Absolutely. So one thing that comes up constantly in tailings projects is density. And honestly, people outside tailings probably underestimate how important density becomes.
Absolutely. In many conventional deposits, grade uncertainty dominates your resource uncertainty. In tailings, it's often density uncertainty. And that really surprises people because tailings density is incredibly variable. It changes with moisture and consolidation, the depth, particle size, the depositional method as well, and the age of the material, how long it's been sat there. And saturation as well is a huge one. You can have a huge density change over very short vertical distances.
Yeah. And I guess the most dangerous thing here is that tonnage can look extremely precise in it, but actually it can be very high uncertainty with regards to that, right?
Yeah. A lot of tailings projects look high confidence because they're closely drilled. But if the density assumptions are weak, your tonnage estimate can still be significantly wrong. And there's another nuance. People often often confuse dry density and wet density.
Yeah.
If moisture isn't handled correctly, you can materially overstate your tons.
Absolutely, that's correct. So this can completely distort your project projections,
Absolutely.
right? And project economies,
Absolutely. Especially for lower grade reprocessing operations where margins are really tight.
Yeah, absolutely. All right, so let's talk about sampling, which is a very important topic when we're talking about representativity of any population that you want to look at. This is where people actually assume that sampling tailings should be easy, but sampling unconsolidated material is actually pretty messy, right?
It really is, yeah. Tailings are difficult because they're soft, often saturated, and easily disturbed. Your sampling method could dramatically affect your representativity.
Yeah.
For example, sonic drilling of vibrocore, auger drilling, trenching. I've seen it where people take like a boat out and try and get it that way. I wouldn't recommend. And they all introduce different biases.
All right. So I guess sonic drilling has become one of the most industry standard methods of drilling that are being used on tailings.
Yes, absolutely. Sonic is probably the best all-round option in many cases, but it's not perfect.
Yeah, it has its own limitations.
Absolutely, absolutely. So you get quite a lot of sample disturbance, moisture migration as well, and smearing up and down the tube. Recovery issues and saturated zones is still an issue.
Yeah. So even though the material is processed, it doesn't necessarily mean that it's easier to sample accurately, right?
Yeah, in some ways it's harder because unconsolidated materials are very different from competent rock.
Oh, okay. So this is where it gets really interesting when we're looking at an MRE perspective. How different is conducting your exploratory data analysis, your variography in tailings as compared to the conventional deposits?
So, it can behave very differently. In conventional deposits, anisotropy usually follows geological trends. Obviously, we've lost those. So in tailings, continuity often follows the beach slopes and discharge locations, spigot locations. It's heavily reliant on the layering and hydraulic sorting patterns. So your variograms are reflecting engineering processes rather than geological processes.
Absolutely. So I can imagine that can create some pretty strange behavior, right?
Yeah, it does. You often see very strong horizontal continuity and very short vertical continuity. Cyclical layering as well. It's non-stationary as well. It can slump and move as it's being settled. And there's abrupt transitions associated with depositional changes as well.
Okay. All right.
Sometimes the statistical assumptions being agreed become questionable.
I get it. Yeah, that's a really important point because a lot of people unconsciously apply conventional estimation workflows that we're familiar with to tailings without questioning whether the assumptions still hold.
Exactly. Tailings are one of the best examples of why copy-paste geology can be really dangerous.
Yeah, absolutely. I agree with that. So you find that one nuance I think people outside tailings underestimate is the role of moisture and the phreatic surface.
Yes, the phreatic surface or the water table is often one of the most important boundaries in the entire model. Above it, material could be oxidized, partially consolidated, can have a lower density, and it's bit easy to excavate generally. Below it, the saturation increases, obviously. The density changes, the liquefaction risk as well is a lot higher, and the sampling behaviour changes as well. So suddenly, hydrogeology becomes directly linked to resource estimation.
Absolutely, absolutely, which is something we typically think about. I mean, we don't think about when in conventional MREs, right?
Yeah, exactly. In tailings, you've got geology, hydrogeology, and geotechnical comes tightly interconnected.
Yeah. So that's one of the most fascinating things about tailings project is the economics often behave differently from greenfield mines.
Yeah, absolutely. In tailings projects, recoverability can matter more than head grade. You're dealing with residual liberation, slimes behaviour, particle size effects, oxidization, as we've said, and the historical reagent contamination can also play a big part. And sometimes you get these very complex mineralogical changes from being sat there for so long. A higher grade zone isn't necessarily more valuable if you can't recover it metallurgically.
Absolutely. So that's a really different different mindset from your traditional mining, right?
Yeah. It is. Some tailings projects are essentially metallurgical projects in disguise of a mining project.
All right, so let's talk about classification, because this is where things get controversial. Can a tailings facility truly achieve measured category?
So that's a really great debate because conventional classification systems focus heavily on like your drill spacing, your drill continuity, and your geological understanding. But in tailings, uncertainty is obviously process driven instead of spatial. So you might have really dense drilling, your assays come back great, or your CRMs are top notch, and you have really close sample spacing, but you don't understand the depositional chronology.
Exactly.
You don't have the faith that you know what's happened and how it's been set down. You can't model the volume properly, and you sometimes don't understand the moisture distribution and density, or the metallurgical reclaimability if you've not done your metallurgical test work on it as well.
Yeah. And I guess the geology as well, because you've lost the geology. So
Absolutely.
you have poor knowledge of that.
Yeah.
So a facility can appear highly sampled, right, while still containing substantial uncertainty.
Exactly, yeah. And that's one of the most misunderstood aspects of tailings estimation.
Yeah, understandable. All right, so now the final topic I want to touch on is why tailings projects are suddenly attracting so much global attention.
Yeah, so there are several big drivers for that. First being the high metal prices make lower grade materials suddenly nice and economic. And the second is critical minerals demand is increasing. So a lot of these historic tailings dams hold a lot of these critical minerals where they previously weren't the mineral that was being extracted, but are contained in the residue that's been left behind. Third is tailings reprocessing can reduce environmental liabilities, and that's huge because these projects can simultaneously recover value as well as improve stability to man-made landforms, and which reduces the closure risk and improves ESG outcomes.
And there's with technology as well.
Yes, absolutely. Yeah.
So the economic case isn't always just metal value, because sometimes it's also liability reduction, rehabilitation value, or permitting advantages.
Yeah, exactly. Tailings projects sit at the intersection of mining economics and environmental management.
Absolutely.
And I think we'll see more of them over the next decade.
All right, yeah. So if there's one key takeaway from today, it's probably this. A tailings facility is not simply a relocated ore body. It's an engineered, evolving sedimentary system with its own geotechnical, hydrogeological, metallurgical, and operational complexities. So treating it like a conventional hard rock deposit can lead to major mistakes. Thank you for listening. So if you enjoyed today's episode, make sure to subscribe, to leave a review, and share it with your colleagues. If you'd like to listen to more of our Fresh Thinking podcasts, you can find them from our free website, Spotify, YouTube, and most other podcast platforms. But thank you very much for joining me today.